nucleus is fixed and the electron at rest orbital will be pulled by the nucleus and it will fall into the nucleus. So therefore, for that purpose, the Rutherford, what he said, the electrons will not be at rest. In fact, they will be revolving around the nucleus. That was his proposal. So for that purpose, he said that no, the electrons, in fact, will not be at rest, will be revolving around the nucleus here. So when he proposed it, he proposed that these electrons, what happen, they'll be revolving. Then, so let's time being, we'll assume that let this be fixed here. Then what were the problems? Now the real problems begin. From how it is possible stability, he just explained that the electrostatic force will provide required centripetal force. So what he wrote is F is equal to Z E square by 4 pi epsilon naught R square. This will provide required centripetal force. mv square by r equal to Fe. Then, so what is the state of this electron? After some time, it will be available here, no? Is there any acceleration? Yes, it will have centripetal acceleration. So though V is constant, V is constant. So then what will happen? It is having centripetal acceleration. I'm just showing. So what is that centripetal acceleration? No? An is equal to V square by R. What is R? R is the radius of the orbit. Then according to electrodynamics, I think by that time Maxwell's theory, very, very important here. Any accelerating charge particle should give out the radiation. According to Maxwell's theory, a accelerating charge particle, Maxwell's equations or theory, what you can call. An accelerating charge particle will radiate energy. So then if it radiates energy, means what energy should decrease, you know, the kinetic energy should decrease. So as the speed decreases, it's going to describe a spiral path. So what is the possible path of this? No longer what happened, it will be circular. So in fact, it will be spiral. So one fine day, what will happen? So fine day in the sense, I think around 10 to the power of minus 4 seconds, what will happen? This electron weapon will fall into the nucleus. But we know what is like. Atom is atom is stable, electrically neutral. There is no problem with the neutral now. The charge of the nucleus equal to charge of revolving electrons. Fine. What about the stability of atom? So according to the this one, what the Rutherford proposed is like electrodynamics. According to electrodynamics or Maxwell's equation, accelerating charge particles should radiate energy. What is the main cause for EM wave? Say why like it's like a, say Maxwell's equation at that time, they were proven practically, and what happens in surrounding what will get influenced. The Rutherford what happened is in mind what happened rather than Planck's radiation law or instead of photoelectric effect what happened, what was there in mind? The Maxwell's equation. That was the inspiration for him. So he was keeping that Maxwell's equation in the mind and trying to give explanation. So there's an acceleration is there. So many asked him, yes, there's an acceleration. Then accelerating charge particles should radiate. So should radiate means what? Continuously should give out photons. If it continuously gives out photon, not only this, continuously, at all points what happen, it will keep on emits radiation. Then finally what should happen? It will fall into nucleus. So one problem with the stability of the atom. Next again, so as energy continuously decreases, the energy of this, what will happen to it? It will decrease continuously. As it decreases continuously, so therefore what will happen? shall we give this explanation for hydrogen spectrum? But when I go and check the hydrogen spectrum is not continuous. So what are the drawbacks of Rutherford? Stability of atom. Unable to explain stability of atom. Second one.
అందుకే ఎవ్వరాను అంటాం.
Think Manideep, huh? Why to unmute? Huh? Unable to explain stability of atom. Next again is like spectrum, hydrogen spectrum is continuous. He proposed here. Drawbacks is hydrogen spectrum is, or unable to explain hydrogen spectrum, will write it. See, hydrogen spectrum is a central theme because from sun's radiation, we are able to trace out hydrogen spectrum. We are able to draw by 19th century only. We are able to draw the complete hydrogen spectrum almost. Any atomic structure, it must satisfy hydrogen spectrum. It's unable to hydrogen spectrum. What is the hydrogen spectrum? It's a line spectrum. And according to the Rutherford model, it should be a continuous spectrum. So it was unable to explain hydrogen spectrum. And next, the stability of the atom. So he could not understand what makes it practically what he knows. Practically, he knows that the electron will never fall back to nucleus. It is there only. But the background, he had idea Maxwell's equation. He was hypnotized by this, better to say. I should not use word hypnotized here. A firm conclusion of Maxwell's equation he had, that accelerating charge particles should radiate. So this having central acceleration. So it must radiate. The direction of velocity is changing. So it will radiate. If it radiates, contingency decreases. Then contingency decreases means what happens that decrease in contingency converted into electromagnetic spectrum. And that is what hydrogen spectrum is taught. But hydrogen spectrum is what? Line spectrum, not continuous spectrum. So here, continuous spectrum. That was the proposal from this one. So therefore, the people they were a little bit in confusion. Okay, charge. See, this is the central idea. This is a nucleus. The whole atom is almost hollow. That one, 99.99% of the atom is hollow. The whole positive charge is very densely concentrated at the center of the atom. That we call as nucleus. That is very important thing. The what all we have modern atomic structure, even still we obey that. That one. And the electrons are revolving about that one. Almost you can say like he has proposed that one. He could not explain how that hydrogen spectrum will come and stability of atom, that one. So Neil Bohr, so he was assigned that particular work by one of his teacher, okay, to study this particular Rutherford, that one. So in 1912, by that time what happened? Planck's radiation law was available. Einstein's photoelectric effect, the idea of photon was available, but matter waves came in 1924. This is a very, very important. The de Broglie, from where he got an idea for matter waves, then Bohr's atomic model. Don't think that first matter waves came, then Bohr's atomic model. No, first Bohr's atomic model came. From 1912, he was proposed. In 1917, the Bohr was able to propose his atomic model. And with that, he was able to explain the hydrogen spectrum. With what the postulates are there in Bohr's atomic model, no? With that atomic model, what happened? The de Broglie was able to provide the matter waves concept. And in 1927, Heisenberg uncertainty principle. And in 1929, practically it was proved. So what we have is a Davison-Germer experiment. I think these are the, once it was proposed, practically proved, no. So then everyone came back to Bohr's atomic model. No, it's something very fundamental, which should not be discarded. So from here is what the whole idea of quantum mechanics has started here. So let's focus on Bohr's atomic model. That is our syllabus. Now you can see that when I get into the description, since why actually according to the original physics syllabus, first we discuss atomic structure. After atomic structure, I should go to what? Photoelectric effect. then matter waves, that one. But here what when we are bringing you in the reverse way. First we are saying the quantization, because if I directly in Bohr's atomic model, if I say quantization, you'll very difficult for you to accept. That's why the quantization idea was introduced for you in the, where like in the matter waves, the momentum is quantized, the matter is quantized, the energy is quantized, Planck's radiation law. Energy quantized, matter is quantized, momentum is quantized. Now here what happened? The space is quantized is what Bohr is proposing. See, all of a sudden, if I say quantization, you'll find very difficult. That's why a prior background is what we have developed for a student.